I'm Wendel Sebastian, full professor of structural engineering at UCL. Natural stone is one of the world's oldest construction materials. Due to its abundance, its high compressive strength, and its durability, stone has been the load-bearing material of choice for globally iconic heritage structures such as St. Paul's Cathedral, which was built from Portland limestone and which still stands proudly after more than 300 years in service. The Industrial Revolution saw a shift in focus from stone and timber to concrete and steel. However, now, almost 2.5 centuries later, there is renewed interest in natural stone because its low embodied carbon shows huge potential to help decarbonize the construction sector in the fight against climate change. Towards that end of a renaissance in stone construction, I'm grateful to the Leverhulme Trust for an award to develop a new research collaboration with Professor Jan Knippers of Stuttgart University. As a core idea within this research, Professor Knippers and I are viewing stone through the modern bifocal lens of digitalization and low-carbon composite structures.
The production of building materials, in particular of cement and steel, is one of the largest sources of man-made greenhouse gas emissions. Therefore, there is an urgent need for a transition towards alternative low-carbon materials. The first choice is timber, and a lot of progress has been made in the domain of timber structures during the last decades. However, timber is a scarce and valuable resource, not available everywhere. That's why we need other low-carbon materials, and one of them is natural stone.
What makes stone a low-carbon material is the low amount of processing that comes with it. So compared to concrete, it only has 3 steps to process it. The first thing being just quarrying it, so cutting it up, transporting it, and just assembly.
Digitalization is an important medium to facilitate communication between professionals along the stone supply chain. Via this medium, structural engineers, architects, construction insurers, quarry owners, stonemasons, carbon evaluators and others can efficiently iterate towards low-carbon construction concepts in stone.
The digital space is a powerful and versatile medium for exploiting the low-carbon potential of structural stone. An architect can define the geometry of a stone structure parametrically in one software, then digitally transfer the data to structural analysis software for use by an engineer, or to fabrication software for use by a stonemason. This communication between professions is seamless, with no loss of accuracy, because the exchanged data retains its integrity.
Professor Knippers and I have explored this idea by setting up a digitally driven exercise on interdisciplinary development of stereotomic architecture in stone. Then, we created an exemplar by using the modern structural invention of prestressing to interlock specially shaped blocks of the French limestone Louget into a stereotomic vault with a flat top surface and an elegant interweaving spherical soffit.
Even though natural stone is one of the oldest building materials, it is almost unknown today for load-bearing structures. Our project shows how a traditional approach as the Abbey pattern from the 18th century can be combined with a contemporary pre-stressing technology and be transferred via digital design and fabrication methods towards a concept for an interlocking stone slab. It allows for disassembly at the end of service life and thus follows circular design principles.
Thanks to modern programmable fabrication tools, we can produce structural stone modules to high levels of dimensional accuracy. Digitalization controls the entire fabrication process. It drives the machine, which transforms the randomly shaped quarrying piece into precision-shaped dimensional stone blocks. It also controls the hydraulic equipment that applies the large forces into pre-stressed block into stone beams, columns, slab, and complex shape like spiral staircases.
At UCL Structural Engineering Laboratory, we are also combining natural stone with timber, another natural low-carbon material, to develop cutting-edge, lightweight, modular, composite floor systems.
In my PhD study, supervised by Professor Sebastian, we have built a large-scale timber stone composite floor model. Both contact sensor and optical sensor technologies have been used in this work to permit recording of the prototype response to load. In tandem with this, a sophisticated computer structure model has been developed to predict the load-bearing performance. These experimentally verified predictions will underpin design guidelines that practical engineers can apply to produce such systems for economic, safe use in practice.
4 months ago, I didn't really think about the carbon embodiment of a building, but since coming to UCL, it's really been on my mind. Stone is a low carbon material because the only embodied carbon within it, from a structural point of view and from a design point of view, is that's present due to the fabrication, processing and transportation of the material. Since learning more about stone and timber composites, I'm definitely more likely to suggest them and try to design them when I'm working in industry in the future.
The usefulness of digital design means you can be incredibly efficient very early on. Yes, you're designing in 3 dimensions as an architect, but also iterating that with engineers to get the columns, beams, and materials down as low as possible. That then is immediately transferred to supply chain. So they cut it, they use the same digital form to cut the stone, the timber as prefabricated elements that come to site. The same model before it's even sent to the cutting machinery is used to then calculate the embodied carbon. And if you're careful enough and it's sequestering the CO2 with timber, that hybrid of stone and timber might actually become carbon negative. And that's achieved by what's called material carbon passporting. So in future, when that building is demolished, you're reusing that timber, not allowing that carbon to be re-released into the atmosphere.
I come from China, a lot of buildings there from concrete, but now I learned a lot about the stone and the timber. They can help the climate change, reduce the carbon emission. Yeah, it's really good.
By enabling my fruitful collaboration with Professor Knippers, this prestigious Leverhulme Award has been a springboard in my quest to pioneer low-carbon construction concepts. I'm pleased to report that, building on the success of this award, I've been appointed a research fellow by the Design Museum Future Observatory, with funding to pursue further research leading to a guidance document on structural stone for architects and engineers. This project will spawn new research avenues for the Sebastian Knippers collaboration, for my dedicated research team of multiple PhD students and postdoctoral researchers, and for my competent technical staff colleagues working in the state-of-the-art structural testing facility that has spearheaded the development of at UCL.